I have hit the recording button. So yeah, welcome to Multilinear Algebra and Tensors. Basically, how to do linear algebra with 3D arrays and other stuff. But one of my pet peeves is that one should not confuse arrays and tensors, but I'll come to that. So yeah, maybe ignore the formula in the bottom, but that's for the end. So I figured I might as well just give some background details on, some just background on vectors and vector spaces. So as a reminder, just a vector space is some arbitrary set V of whose elements we call vectors. And it's coupled with a field, so a scale essentially is something like the real numbers or the complex numbers. Numbers that we can add and multiply, and we can take inverses, both for the addition and multiplication. And then we have an operation that we can add vectors together and we can multiply vectors with a scalar. And these two satisfy. So if we just take the vectors of this plus operation, this has to be a commutative group. So I can add vectors and it's associative. I have a zero vector that acts like a neutral element of my group. And I can find the opposite vector for any vector I take. And I can swap the order of my vectors in the addition. And then this all plays with scaling my vector with some arbitrary number. And again, it has to satisfy some properties. So on the first two are distributivity. And so as a result of these, I have that, okay, if I multiply by the unit neutral for my field, that's the same as doing nothing. And then if I multiply with -1, so the opposite of the unit, that's essentially the same as taking the symmetric element relative to my group operation on my vectors. So that's reminder one. Now that's vectors as they're defined, but most people, and most of the time when we encounter it, we use it through a basis. So a basis of a vector space is just a set of vectors such that for any other vectors in my space, I can uniquely express it as a linear combination of my basis vectors. And typically, so if V is the vector I'm trying to express, I'll find some scalars Vi, and note here that, okay, I'm already writing the indices on the top. This will be very important later. So I'm writing V as a unique combination of Vi times my basis vector Pi's. And it has to be unique, and so not every set of vectors will satisfy this. And okay, the next thing is, instead of writing this sum, you could imagine, okay, I'm writing just I in some set I of indices, but it could be I from 1 to n, just the same. And it's very common when working with tensors to just not write this sum part and just only write the symbols. And the rule for this, how to interpret it, is if I have any indices that occur multiple times, that means I'm summing over them. And I think that's sort of how stuff like libraries like einsum work. And another notation for a vector, at least, is writing this as a column vector. And here I'm writing the relative to the B basis on the bottom right here. Usually we don't. But yeah, keep in mind that when you have a column vector here, it's usually up to some basis. And so that's something that's very easy to confuse between a vector and its representation with respect to some basis. And speaking of basis, we can change from one basis to another. So if I have decided that, okay, I have another basis beta j for bj tilde, and that I obtain from applying some linear transformation to my original basis vectors. So Lij here is essentially a matrix those are essentially the coefficients that let me represent my vector bj tilde with the original basis vectors. And okay, if we look at our vector v, we know that it can express this. We know that we can express it in the original basis with the coefficient vi. And the trick here is, okay, because I can insert the identity matrix, and okay, let's say that I'm inserting this lambda, which is the inverse of my matrix L here, and multiplied with the Lij, so my matrix. So this whole block should be equal to the identity. But here I'm separating them because I'm using the fact that I know that by definition, this Lij bi term is just my beta b tilde j by basis vector. And so that means that this part here must be the coefficients in my new basis. And so I have that v tilde j is equal to the inverse matrix. So my inverse matrix times my old coefficients. And so notice that for when we change from one to a new basis with some matrix L, the coefficients, they had to change by the inverse matrix. And so when that happens, we say that basis coefficients are contravariant. And so I'll stick in the rest of my slides. I'll use orange for things that are covariant, so they change with the basis. I apply the same transformation. And in blue, I'll use for stuff that's contravariant, so I have to change with the inverse of that matrix. So another background slide. So if I have a vector space, I can construct the space of linear forms on it. So a linear form is just a linear function from my vector space to my field. And okay, here, let's just, instead of k, just imagine it's the real number, so r. And so yeah, it's just any function alpha that takes a vector and returns a scalar, and that has to be linear with respect to its argument. And this is actually a vector space too. And so okay, it's a vector space called a dual space, and it has some nice properties. In particular, if vector space has finite dimension, then my dual space has the same dimension. It has essentially it's isomorphic at this point. And okay, if I take some basis of my original space, I can construct a basis of my dual space. So beta I with indices on the top. Simply, so these beta I mappings are simply applied by, if I apply it to some arbitrary vector v, that would just be the ith coefficient, the ith coordinate in the basis. And so that means that when I apply bi to some, so beta I to some bj, that's essentially this delta ij, which is the Kronecker symbol, or here it's essentially the identity matrix. And so this is these beta i's are a basis of my dual space. And so I can write the coefficients, so with alpha i's, and notice that, okay, the indices are on the bottom. So that's a convention that covariant indices are on the bottom and contravariant indices are on the top. So usually we don't have colors, we just have top or bottom. And as a sort of, maybe not notation, but I like to call these covectors to differentiate them from vectors. And you can also write them as a column vector, or another column, a row vector, if you like. And okay, I mentioned that these are, I called those in orange because if you look at if you try and change the basis, then okay, after some calculations, you do find that these coefficients in my dual basis are covariant. They change with the basis. So I just apply this Lij matrix, which is the same as I applied to my original basis vectors. So far, so good. So yeah, recap, and forgive me for insisting on this, but I know from experience that this is something that trips up. People get really tripped up about this, and so it's important to get the hang of it. So yeah, my vector space basis can change with some matrix L. I have my dual basis, which will change with L minus 1, so the inverse. And then if I try to express my vectors in this basis, then in the vectors I have contravariance coordinates because they change with the inverse matrix. And on the dual space, my coefficients will be covariant. So, cool. So now we can actually get to the new stuff. So this wasn't part of the reading, but it's a good example that's also in the source. So we can define what's called a bilinear form as just a function that takes two vectors this time, and it has to be linear, but in each, so it will be linear, but in each input separately. So that's why I have on the first one, if I have some linear combination of my second argument, that boils down to, I can separate it by linearity. Same thing if I have a linear combination in my first argument, but it does not have to be, and usually it is not linear in both arguments or in both arguments at once. And so that's where things stop. And okay, one way I can construct one such a bilinear form is by taking two one forms, or so dual vectors here in this case, and taking what's called the tensor product. So usually it's noted with this circled x. So alpha tensor product beta applied to u and v, because it takes two vectors, it's simply the product of a applied to u times b applies to v. And okay, so far so good. This is in UK, so it's easy to check that this is in fact a bilinear form. And in fact, it's what's called a rank 1 bilinear form because it's just a product of two. Same way you have rank 1 matrices. And I can find a basis for this vector space of bilinear form. So it is a vector space too. And I can construct its basis by simply taking these inner products of my dual basis elements. So then again, I can find the coefficients alpha ij simply by applying alpha to my original basis elements, and those coefficients also turn out to be covariant, so they change with the basis. Now, a very sort of useful and important example of a bilinear map is the inner product. So an inner product is technically a bilinear map, or bilinear form, sorry, that is also symmetric. So if I swap the order of my arguments, it's equal, and it's positive definite. So apply to v two times, it's greater than 0, and if it is equal to 0, then that means the input v was 0 as well. So the classical example is simply the inner product in the basis, and so that's just okay, the sum of ui vi. So remember, it's a sum, and if you want to be precise about it, okay, we have to add this Kronecker delta ij, but covariant in this case. So that amounts to taking this sum. But in general form, we can replace this delta ij by some arbitrary gij. And if you were to write this gij as a matrix, like you would, because it has two indices, this would be so the condition for it to satisfy these two axioms is equivalent to saying that this matrix is symmetric positive definite. And so again, I can evaluate it as is on the previous slide. And this so inner product, or sometimes you call it the metric, it's very important in Riemannian geometry because it's the main tool of how to describe these Riemannian manifolds. And so this is actually the main reason, the main area why people care about multilinear algebra in the first place, because it's a necessary language to describe Riemannian geometry, but in a more complicated way, because you usually do not have just one, but you have one per point of your manifold. So yeah, that's the main reason people care about multilinear algebra, and it comes up all over the place in physics. Okay. Now we can move on to just general multilinear forms. So a k form or a k linear form will just be a function that takes k vectors, and that is goes to R and is linear on each of those k vectors separately. And just as for bilinear forms, I can create a basis for it by simply taking my tensor products of k basis elements. And generally the notation will be, okay, T, my multilinear form will be simply expressed by these coefficients, Tik, I guess. This should be orange, not, oops, sorry. This should be covariant indices. So you have covariant indices describing my k-linear forms, and I express it in my basis element. And to give another example of such a k-linear form, the determinant, so if I take my n vectors in Rn and just pack them up in a matrix, that gives me a square matrix, and I can take the determinant of it. And if you remember some properties of the determinant, you can see that it is indeed linear for each, like for each column or each row of my matrix, the determinant is linear, but overall it is not. And this is another property. So if you want to express the determinant here in your basis, okay, you can do this complicated thing. But notice that I see this, essentially my coefficient is just sine of my indices, and this function sine, so okay, it's 1 if the set of indices I1 to In is a even permutation of my indices, or -1 if it's an odd permutation, or 0 if it's not a permutation at all. And that goes back to the fact to it, okay, if I take my matrix and I permute two columns, I multiply by -1. Same thing if I multiply two rows, or sorry, swap two rows. And this is sort of one thing that is not mentioned in the source, but it does come up whenever people talk about multilinear form, is about symmetric or anti-symmetric linear form. So remember, symmetric, we saw that for the inner product, changing the order of my argument did not change the result. Anti-symmetric, as is the case for the determinant, is the opposite, is that if I permute by an even permutation, the result stays the same. If I permute by an odd permutation, the results change sign. Okay, so that was one example of a k-linear form, and we can actually cook up any number of them just using whatever coefficients we like. And as with, so remember, we originally constructed my initial example of a bilinear form by taking the tensor product of two one forms, and I can take easily the tensor product of two k forms, or even two. So if I have a k form and an L form, so T is my k form, U is my L form, I can take the inner product, which would be a k plus L form, so to take k plus L vectors, and it's very simply defined as you would expect, as taking so k plus L vectors and applying T to the k first arguments, and taking the product of that with the U applied to the L last arguments. Okay, so far so good. What about, so right now we've been working with k forms, they're all covariant tensors because their indices are always covariant. What about contravariant tensors? And so to do that, we have to remember another thing from linear algebra, is that if I have a vector space V, I can construct this dual space V star, and I can take the dual of the dual, called the bidual, and as luck would have it, at least in finite dimension, the dual of the dual is isomorphic to the original space V. And in particular, we have it's not necessarily the case in infinite dimensions, unfortunately. Usually you can get more elements in your so it's always the case that you can embed any vectors in your primal as an element of the dual of the dual, but you can get some extra elements in the bidual. But yeah, it really depends on what your space looks like and the cardinality, and it gets pretty hairy. So yeah, at least assume it's infinite dimensions, and we say sane. In infinite dimensions, all bets are off. Okay, so yeah, so the canonical isomorphism between the dual and the original space, simply okay, I can take my vector v and map it to some element of v star star, and it simply okay takes my dual element alpha and simply applies alpha to v, and that's a linear map on my dual space. And going the other way, at least in finite dimension, is fairly easy because in finite dimension, because I can embed my vector space in my bidual space, and they have the same dimensions, that means that the map has to be invertible. Or at least that's the main gist of it. And okay, I can, so now I have my contravariant tensors, because the thing is that I can sort of construct because my original vectors can be interpreted as, okay, not just vectors, but functions that take covectors and return scalars and are linear. I can also do this tensor construction for those as well, and so I can define my tensor product of two vectors u, so o dot, no, not o dot, o times v applied to my forms a and b, alpha and beta, as simply alpha applied to u times beta applies to v. And those are indeed an example of contravariant two tensors, because my indices will be given by this Sij with ij contravariant indices, and my basis elements being simply the tensor product of my basis elements of in my original vector space. But note that here it's always by isomorphism. So whenever we're working with tensor, there's always this sense of things are equal up to some isomorphism, and it usually makes things a little bit easier. So okay, we've seen K-forms, we've seen contravariant tensors. Let's now talk about arbitrary tensors. So we can define some arbitrary tensors, so a tensor of type PQ, as a linear form that takes P vectors in my dual space, or P covectors, and Q vectors, returns a scalar, and is linear in each of them separately. And I actually have a whole range of different things. So typically the convention is if I have a tensor of type 0, 0, that's a scalar, because it has no indices. If I have a 1, 0, that's a covector. So we know that as well. 0, 1, that's a vector with contravariant indices. And then the next row, okay, I have 2, 0, that's a bilinear form. On the middle, I have a tensor of type 1, 1. So that you can say, okay, it's a function that takes one vector and one covector and returns a scalar. And if you think about it for a little while, it's actually the same as a Lie map or as a matrix. And the way to see that, if you think of a matrix as a map from my vector space, so that takes a vector to a vector, well, if I just carry it, if I use terms from functional programming, if I carry my operation by applying a vector, so if I multiply a vector, I get this vi on the bottom, so I have to sum over my contravariant indices, and all that's left is one covariant index. Nope. I have to sum my j with my I. So it would be clearer if I. Right, so let's say I multiply with some vector vj. So these are my coefficients. I'll be summing over the j index, and so all that will be left is just a thing with one contravariant index, and that's just a vector. So we can. It's really like, I think it really helps to think of this in terms of functional programming as functions that you can carry, so functions that take multiple arguments, and you can carry them in in whichever order you want, and so on. So I have essentially a pyramid of tensors, and generally the notation will be something like this. So I have T with P contravariant indices, Q covariant indices, and again I have these basis terms of first my my contravariant basis elements and my covariant basis elements. Cool. So we know how to take tensor products of tensors, or at least tensor product of vectors, of covectors, and arbitrary tensors. And as a derived notion, we can talk about the tensor product of two vector spaces. So if I take two vector spaces V and W, and let's say that V has dimension n and W has dimension m, then I can form the n times m dimensional vector space VO times W. And the basis for that will be given by BI O times AJ, where BI is my basis for V, AJ is my basis for W. And I can just write the basis down as, or at least my indices as the following. And notice that I have something that I have two indices, and you can be tempted as to say that, okay, when I have something with two indices, that's almost the same as a matrix. And this goes a little bit further, because so if I take my space of bilinear forms, so from V, so V cross W, so this is just space of functions that take two of each and are linear and so on. So this is a bilinear form. I can carry it, just give it one argument, and that becomes a linear map from V to the dual of W. Okay, this whole part might not be super clear, but it's explained much longer in the text. But bear with me when I say that this space of bilinear forms is isomorphic by carrying to the space of linear maps between V and the dual of W. And those would be the space, if this were R, you could say it's R M cross N, so M cross N matrices. Whereas, actually it might be the other way around. Yeah, I think it is the other one. So N cross M and M cross N on the bottom. So I have some space of linear maps, and I can swap the two. So because I have the same dimension, they are isomorphic. And again, because I have the same dimension, this is isomorphic to the tensor product of V star and W star. And by some trickery, I can say, okay, it's just the dual of V O times W. And this itself is just isomorphic to the space of linear maps from the tensor product VW to R. And really the most interesting is this connection between the first, where I have bilinear maps, so the maps that are linear but with respect to each argument, and linear maps from my tensor space. And so it's nice because it means that anytime I have some K form, I can always reduce it or think of it as just a linear map on some tensor product space. And this is pretty useful in many contexts, because I can just keep or just change the space I'm working with and just stick with linear maps. Okay, so some few things before an example as some bonus. So just like I can take these spaces or tensor products, I can say, okay, let's take my PQ tensor space by simply taking the tensor product of P copies of V and Q copies of V star, and one space of particular interest for the tensor power, which is simply taking P copies of my vector space and taking the tensor product of it. And so that would be just TP0. And the total nice, but this is technically a bit more advanced, or bonus if you will. We can actually form what's called a tensor algebra with this by taking all possible tensors. So that's why I define this tensor algebra TV as this infinite. So this O plus sum is called the direct sum. So the direct sum of two vector space is just, you can imagine just taking two vectors in one vector of each space and just sticking them together but separately. So it's like concatenating them, if you will. So I'm taking my direct sum and I'm actually taking an infinite direct sum of my tensor powers. And so it looks a bit like, okay, I have first because I start at 0 by convention, that would be the scalar field. So let's say real numbers. So I have elements that look like real numbers plus a vector plus 2 tensor plus a 3 tensor and so on. And it looks a bit weird because so I mean, okay, my elements look a bit like this, right? I can have scalar plus a vector plus a matrix. And which you say, okay, we can ask, okay, what does it mean to add? Well, it's just add it. It's like there's quite a bit of a Haskell vibe to it. So yeah, it's like one vector space to hold them all, because I'm taking a single vector space with all my possible tensors, or at least all my tensors of one type. Then I can extend it to add more, so you can have some fun with that. And I mentioned it's an algebra, so as a maybe not so a reminder, but an algebra is just a vector space with some vector product, so a product that takes two vectors and gives another vector. And in particular, it has to be bilinear, or at least linear with respect to each input. And so you can say you can define these vector products as just a linear map from the tensor product of your vector space to V. And I claim that if I take the tensor product on this very strange space, I have an algebra, because I have a product of two vectors that gives me another vectors. It's associative. There's a neutral element, and so on, but usually no inverse. So that was more the thing to expand your mind. So I do have an example relevant to machine learning in this case. So thanks to Dashiell for linking this one. So it's from a paper by Anthropic on transformers and interpretability. And they use this tensor product notation to interpret, or at least to give some interesting notation about transformers. So I remember, I think pretty much most people know how transformers work at this point. So I have my tokens that I embed in my embedding space by some matrix, and that gives me a sequence of embeddings that each get mapped through first some attention heads, so H0, H1, etc., in parallel, and those get added back to the original embedding. Then I also run it through a multilayer perceptron, again element-wise. And so this would be just a single attention block, and there would be multiple attention blocks. And at the end, it would go for an embedding matrix to get my probabilities back, or my tokens back. And they note that, okay, this is nice and all, and we can sort of write explicitly how these attention heads work. So I first have to take my key, query, and value vectors by taking my so xi from the residual stream, as it's called, and applying matrices different. So yeah, I have these three matrices I apply to it. And then, okay, I can form my attention matrix A by taking the softmax of QT, Note that this Q and K is a matrix because I'm taking all of these vectors, and so this really is a matrix. So this is a square matrix for all my different all the different tokens in my context. then the result simply the linear combination of my attention matrix times the value vector. And then at the end, I have some, I run it through some output to go back to the residual stream. But usually we have multiple attention heads, and so typically people just write this big old matrix W output for the heads by simply concatenating my individual matrices here and multiplying with these the result vectors. But we can do a little bit better than that, because technically what we're looking at is a map that takes a matrix, right? The matrix being my element xi, which is has dimension the number of the context length times the embedding dimension, and I want to find a linear map from this matrix to another matrix of exactly the same shape. And so, okay, if we want a linear map between two matrices, that's actually a 2-2 tensor. And so we can write it down. And eventually what it works out to be is basically first, if we read from right to left, right, I first apply the tensor product of the identity matrix times my value vector. And here the identity, I guess, would be identity of size to context length. And so if you take this inner product and compute it, you can think of it in block form as just almost like an identity matrix, but with blocks. And each time I have a block, it's just the WV matrix. And so this is my first step. Then I compose it by matrix multiplication with the tensor product of A times I. So this is a bit different because now, instead of having all my blocks on the diagonal, I have blocks, each of the a scale entity, and I scale it with the elements of A. So I have a first block AI, which is A11, which is a scalar times an identity matrix, then A12, which times an identity matrix, etc. So that's my second operation, and then I compose it again with just a tensor product of I times my output matrix. So notice that whenever I take the tensor product of the identity matrix with some matrix that's almost like a linear algebraic representation of running some things in parallel. And in the end, actually, there are some nice formulas about the tensor product and composition that lets us rewrite this whole expression as simply the tensor product of A times the WO times WV, which sort of makes sense if you look at it for long enough. So that was the example. I unfortunately could not dig very far into this for reasons, but we can discuss it if you want. Which leads me to the bonus. So I left it as a bonus exercise when giving the reading of trying to come up with a unified product that generalized both the inner product, the outer product, and the tensor product. And it had to be at least, so first it had to be well-defined, and second it had to be associative. So yeah, I have the solution here, but it's a bit informal, but it's nice enough because it gives meaning to some of the stuff we've been talking about. So here I won't necessarily use my coefficients, I'll just use column vectors to describe vectors or contravariant indices, and row vectors, called in orange, to denote covectors or covariant indices. And then I need another rule to describe matrices. And I'll say that a matrix, I can interpret it either as a vector of covectors, so that's why the outer parenthesis is blue, and I have two covectors inside, so a vector of covectors, or the other way around, a covector of vectors. And the rule is that I can sort of swap around between interpreting something as a vector of covectors or a covector of vectors. And so yeah, generally I can swap covariant indices with contravariant indices with no problem, but I'm not allowed to swap between indices of the same type. That's not allowed. But just keep this picture in mind. And so I can define rules for taking products. Okay, I'm only taking 2 elements, but it should be able to, it shouldn't be too tricky to generalize. So the first one is the one we know and love, the inner product rule. When I have a covector times a vector, that's simply the sum ax times by. Then the outer product rule, if I have a vector times a covector, that gives you a matrix, simply being by ax, ay, bx, by. And already this outer product rule sort of fits in the tensor product, right? Because I have a one tensor, and I get a 2 tensor in the end. But note that we haven't formally defined what it means to take the tensor product of a vector and a dual vector. And okay, then I have these 2 additional rules, which are essentially directly derived from the tensor products, which is if I have the product of 2 vectors, I define it as simply, okay, I have a vector whose first element is a times my second vector, and the second element is b times the same vector. And those you can actually write in terms of the inner product, the tensor product, no problem. And then it's the similar kind of deal for the covectors, but instead of having my scalars from the left, here I take my scalars from the right. And these rules, I claim, let us do some interesting stuff. So in particular, we can check that I can compute the matrix vector product using my rules and that it should be consistent. So for example, if I have a matrix times a vector, well, I can first interpret my matrix as a vector of covectors and use the rule for the product of 2 vectors, and that then maybe some inner products in my element, and so have the result as I would expect. And I could do the same as before and just interpret my matrix as a covector of vectors, apply the rule for it, and if you do the calculation, it works out as well. And we can do exactly the same for a covector times a matrix, and it works out the same. So far so good. It seems to be well behaved, that these rules lets us, with a single notion of product, have all these nice operations. But now, here's a nice thing. Okay, have you ever wondered what does it mean to take the product of a matrix with a covector on the right? And okay, we can actually apply the rules. So let's say first I start by interpreting my matrix as a covector of vectors and apply the rule for it. And I get what's essentially a 2-1 tensor, but note that I need to be flexible about the order of my covariant and contravariant indices. So that looks like a covector of 2 matrices. And if I go the other way around, I interpret my matrix as a vector. Again, I get something that looks like a covector of, or it looks like a matrix of covectors, but I can swap and get it to be the same as a covector of matrices. So far so good. And I can do the same as before, taking a vector times a matrix, and it all works out. So yeah, this was more a bit of fun on my part, because it's not necessarily a practical thing to do, but it's sort of fun, at least I found, to like represent these vectors and covectors in this way. So yeah, that's all I have, at least in terms of slides.